To start out with, I'll take a quick look at the current state of HBase, and from there we'll dive deeper into coprocessors and look at how they provide a whole new interface for interacting with data that you have stored in HBase. From there, we'll continue on to looking at HBase security, both as a feature in its own right, and also as an example of how to make use of some of the capabilities that we provide through the coprocessor framework. And finally, I'll leave you with a few links to more information to get you started if you want to start working with these tools yourselves. So HBase is constantly changing. The next coming release of HBase will be 0.92. I won't give you an exact date for that, but hopefully we'll have some release candidates out in the next month or so. And that will contain a number of features: distributed write-ahead log splitting. It'll contain support for running on top of more versions of Hadoop, a tool for decommissioning region servers, the coprocessor framework that we'll talk more about in just a minute, and many more, of course, bug fixes, documentation improvements, all that good stuff. Following the .92 release, we'll be working to incorporate security, and there's a whole lot more coming in the pipeline for performance, as well as a new internal file format for HBase and other fun stuff. So coprocessors, like HBase, Hadoop itself owes a lot to Google technology. Bigtable coprocessors were first described by Jeff Dean as a framework that allows user-level code to run in place with data in each big data tablet server. It also provides a client library that gives a high-level call interface, so clients can just make calls to a row or range of rows stored within Bigtable, and the coprocessor code will then execute against that data. For HBase, we've taken this functionality and applied it the same tools, but with a little bit of a different twist. We've taken this as a means of extending HBase functionality itself and really giving you a modular, loadable framework for plugging in your own functionality. What this means is you can really leverage HBase as a platform for scaling and distributing your own application logic the same way you can use it to scale and distribute your data storage. First part of the coprocessor framework we call observers. You can think of these as very similar to database triggers if you're coming from a relational database world, in that we provide event-based hooks to interact with all kinds of standard operations going into HBase. But in addition, you can override behavior of core HBase code and extend it or customize it with your own functionality. The first type of observer is region observer. This gives you hooks for interacting with standard CRUD or DML type operations. From HBase client perspective, this means gets, puts, scans, deletes. Each region observer can flag to the framework whether it wants to substitute its own results for client requests and return those directly, or it can override the standard core behavior of HBase. The second type of observer is master observer. Similar to region observers, this provides event-based hooks, but for interacting with metadata type operations or cluster administration operations, things like table creation, modification, other types of things that the HBase master coordinates. And the third type is a write-ahead log observer. This gives you hooks into appending entries to the write-ahead logs, as well as to the execution of restoration of those write-ahead log entries. But an interesting implication of this is you can leverage, again, the robust write-ahead log infrastructure of HBase for your own application level purposes. Append your own entries to the log and achieve the durability guarantees from that, as well as make use of the recovery mechanisms in the case of server failure. So when a request comes into HBase, you can have multiple observers loaded against a particular table. The request will come in to the region server and be handed off to the pre-hook associated with that request for the first loaded coprocessor. Coprocessors can be loaded in different priorities, allowing you to identify certain types of coprocessors as more definitive, and we use this functionality for security in order to authorize requests before they continue elsewhere. So each of the loaded coprocessor pre-hooks gets called. Then we continue on to normal HBase processing, in this case the hRegin get call. Finally, post-hook gets called on each loaded coprocessor, and then the result is returned to the client. The second aspect of the coprocessor framework is endpoints. And these provide you with the ability to export your own custom RPC protocols to clients and give you a standard interface for making calls over those. You can think of these as analogous to stored procedures. Like region observers, these are loaded against the table regions in HBase. What this means is that your own custom code can execute in process directly against the region data. So when you combine this with region observer, you get a really powerful combination. A region observer can watch data as it comes in or changes, maintain some kind of state itself, and then you can expose your own custom semantics for interacting with that state, querying it through an endpoint protocol. As I mentioned before, clients make a call over a single row or range of rows, and the coprocessor framework will transparently split those calls into a separate RPC per table region, and then combine the results at the end to return to the calling code. And we have, hopefully you can see an example of an endpoint request actually executing from a client to the server side. Green represents user-level code that's executing. Yellow is HBase code. Blue is the table regions. So we have a sort of contrived example of this row count protocol that's being exposed. The client just calls a normal method against that protocol. HTable coprocessor exec splits that into multiple parallel RPCs and then returns the results either as an aggregated map of results, or clients can also be notified via a callback interface as individual RPC responses come back in. There are a few different projects making use of coprocessors currently. The security implementation I'll talk about in just a minute. There's also a really interesting project to embed Lucene indexes directly in HBase region servers that a guy, Jason Ruthergren, is going to be talking about tomorrow at the HBase contributor meetup, if any of you are going to that. It's really interesting stuff going on. That makes use of a region observer to update the embedded indexes as data changes, and it provides a custom protocol for executing searches against it. Finally, we have a set of standard aggregate operations in HBase trunk that allow you to do sums, averages, these things against your existing table data. The future of coprocessors, well, it really depends, as how far your imagination goes. There's been talk of building parallel computation framework based on coprocessors, either exposing the MapReduce API or some other parallel processing API. There's been talk of embedding a JRuby interpreter, allowing you to execute dynamic script fragments against your table data. And there's been a lot of interest in building some form of eventually consistent secondary indexing, using region observers to queue up index updates as the underlying data changes, as well as persisting records of those index updates to the write-ahead log using the wall observer. and providing consistency guarantees via that. So moving on, I'm going to talk about security. First, a small bit of history. 2 years ago, there was very little in the way of meaningful Hadoop security, but a lot's changed in that 2 years. If any of you were here last year, there were a few talks on the initial implementation of secure Hadoop, and strong, robust implementation of secure Hadoop has really made it possible for us to address HBase security as well. So we've built on top of that as a foundation. Why are we doing this? Well, there's been this kind of common trend towards shared computation clusters. Trend Micro is no different. We want to have shared resources that all of our groups can leverage, but to be able to do that effectively, you need to be able to control who has access to what. So it's all about enabling multi-tenancy for our internal groups. So our initial implementation has addressed a few high-level goals. We want strong authentication of HBase clients. It's a default deny policy. Your data is private unless you explicitly grant access to it. We provide access control lists where access can be granted at the table, column family, or individual column qualifier level. And assuming you have the rest of the security infrastructure set up, meaning Kerberos and LDAP, which are not trivial in themselves, the HBase administration piece of it should be relatively simple. We've left a few things off on the table for that. We are not trying to address either row level or per value ACLs at the moment. All of the HBase files are actually owned by an HBase system user in HDFS. So we're not trying to push down table ownership to individual HDFS file ownership. And it's really just an initial discretionary access control implementation at this point. We're leaving full role-based access control for a future project. So for implementation, we've built on top of the secure RPC that work that has gone into Hadoop. So we've ported over the Hadoop RPC changes as a loadable engine. One of the overriding goals for our implementation was all of security in HBase should be optional. We don't want to impose any performance overhead on people who are not interested in running with security enabled. So all of the pieces you'll see here have been designed as optional loadable components. The RPC engine provides SASLAuthentication of clients, both Kerberos GSS API based, as well as a digest MD5 implementation that uses signed tokens for MapReduce clients. Again, very similar to what Secure Hadoop provides. Authorization is performed by a loadable coprocessor. And for there, we have a simple list of permissions that can be assigned to users or groups, again, at the table, column family, or individual qualifier level. Finally, those first two are pretty meaningless if you can circumvent security via another avenue. So since HBase relies heavily on Zookeeper for normal operations, we've had to produce a secure version of Zookeeper as well in order to lock down the entire stack. So the real heart of HBase security is this access controller coprocessor. This serves two different roles in HBase. It provides interaction for granting, revoking, listing assigned permissions. It also performs all the authorization checks for requests that come in against table data. So first, let's look at that first role. In that instance, access controller functions as a coprocessor endpoint. So it defines a custom protocol that it exposes to clients. It's the aptly named access controller protocol. That defines three simple methods. In order to interact with that, clients first obtain a reference to the underlying HBase table where we actually store the ACL assignments. They then call the htable coprocessor proxy method, and that returns a dynamic Java proxy object that will serve as the dispatcher for those RPC requests. The client code can then simply call methods on that proxy object, and those are translated by the coprocessor framework into individual RPC calls that are sent to the region server. The second aspect of Access Controller is the region observer and master observer implementation. And we use that to perform all the authorization checks we need to ensure that a client making a request to HBase has permissions granted to be able to do so. So in this case, a region observer and master observer define a number of hooks that you can implement. We implement all the pre-methods that get invoked before normal processing. In this case, you see an example of the pre-get method. So when a GET request comes in, Access Controller checks, does the client making the request have permissions to read the bit of data that it's requesting? If that succeeds, it continues on. If it fails, we short circuit processing and return an exception directly to the client. This is what that looks like. So the client request comes in, Access Controller pre-get gets called. This is all prior to normal HBase processing. If that succeeds, then we continue on to any other loaded coprocessors. If that fails, we short circuit, return the exception directly. Then we continue on to normal HBase processing. Finally, the post hooks get called for any loaded coprocessors, and the result is returned. The final part of the security implementation is secure Zookeeper. And as I mentioned before, Zookeeper really plays a critical role in both in standard HBase cluster coordination. It serves as a notification mechanism for server failure. It's key in region assignment. It also allows clients to find the root catalog table, which then allows them to look up the location of their actual table data. In addition, the security implementation also relies heavily on Zookeeper to coordinate changes to the access control lists throughout the entire cluster. So obviously, if you can go directly into Zookeeper, modify those access control lists, we're not providing any real security. So we need strong security, or the entire stack can be exploited by means of Zookeeper. So for the first portion, we've provided a new authentication provider for Zookeeper. And this enables SASLAuthentication of clients, again using Kerberos GSS API. Separately, a background thread runs to update client credentials for long-running processes. And another configuration option of this is clients can be allowed to continue to access Zookeeper even if they're not authenticated. This is useful for running a mixed mode kind of usage of Zookeeper, where we can still restrict access to sensitive data via Zookeeper ACLs, but we don't have to go through the overhead of configuring Zookeeper client access on each potential client machine. So we found this useful ourselves in rolling out security. And this is how that actually looks. So you see an HBase client running that can access the kind of public HBase znodes that are exposed. These are really the only things that an HBase client needs to be able to function normally. But at the same time, more sensitive data is secured by means of a Zookeeper access control list, so to only clients that are SASL authenticated as the HBase user. So this allows us to restrict access to those znodes to the HMaster and region server processes. So currently we have security deployed and running in production for our internal groups. This allows us to kind of validate the current implementation, verify it really works in real usage. The next steps are to ensure that we get all of the work that we've done upstream to both the HBase and Zookeeper projects. All of the code that I'm talking about here is currently publicly available, but there's obviously a lot of work to do to go through the normal community review process, as well as ensuring that it can be incorporated into HBase in a way that doesn't really impact people who are not interested in running security. We'll also be posting some more blog posts and information about how to get this up and running yourself if you're interested. There are some links on here to additional information, a couple blog posts and the code. Color scheme did not come out so well, but you can view that online later. All right, that's it for the talk. I'm open to any questions you have.
Hi. Sorry. I have two questions, actually. First was, is the Java API the only way of granting permissions, or is there like shell commands or anything?
There are shell commands that use the Java API themselves, but it's a simple grant, revoke, list permissions commands in the HBase shell.
Okay, thanks. Other question was, how does it affect performance?
We haven't specifically quantified performance impact. It's going to depend a bit on the application, but as far as actual overhead, we've done some profiling. I would expect somewhere maybe 5, definitely less than 10% overhead.
Great, thanks.
Hi. The HDFS file permissions, do you set these to owned by HBase user and 700?
Right, so the question is for HDFS file permissions.
Yeah.
So I kind of breezed through that aspect. The HBase processes themselves run as a specific user.
Right.
So we're running as the HBase user.
Right.
So the entire HBase directory is owned by that HBase user. And it does the reading and writing from those files directly. You can isolate that from any other processes or access you have running. And then interaction through the normal HBase API is mediated by the access control mechanisms.
Right, but if you do that, for folks who want to access directly those files without using HBase, they won't be able to access it, correct?
So you want to read H files directly without going through HBase?
The actual metadata, not the metadata, actually the data that is stored on the HDFS itself. If you have one HDFS file data.
Do you mean the HBase files stored on HDFS or other
That's
files?
correct. Yeah.
Well, normally we would not suggest reading H files directly from HDFS. As you make updates to data stored in HBase, it goes first to a memory store. So there's no guarantee that the data you're reading from H files is actually up to date.
Okay. So it's better to completely isolate both of them.
For reading, I would not go directly to H files. I would always go through the HBase APIs.
Okay, thanks.
Hi. I was wondering if any of the actions put or get that are triggered in the pre or the post phases will initiate triggers again. So is there any sort of cycle detection that you guard against?
So if you were, say, doing your own put through...
If you did a put within a coprocessor, what would happen? And it went to the same region server, would you just potentially go into a loop, or?
We don't do any explicit cycle detection looking up the stack of where it came from. We do provide some internal, as part of the framework, some internal APIs for accessing both region server services, master services, as well as interacting with tables. So I would, if we ran into issues there, I think we would evolve those internal APIs. In general, we would discourage using normal HBase client operations in coprocessors. For any distributed system, if you're doing something that potentially opens a new RPC connection to another server, you're running some kind of risk of distributed deadlock.
I missed the first couple minutes, so I apologize if you already spoke to this. Is there any similarity to Percolator, Google's Percolator in coprocessors?
Well, Google's Percolator I know uses coprocessors. I don't know much of the details of Google's actual implementation of coprocessors, because I think the information they've made public is fairly limited at this point. We've taken the general ideas that they presented, but we've applied them with a slightly different focus. One of the things we saw in HBase is people wanted to make use of it in different ways. So they would be extending core classes to provide that functionality. So part of the goal of coprocessors is to enable a kind of loadable means of extending that functionality without having to directly subclass core code. So I don't know if that directly answers your question.
Well, just in the sense that HBase was maybe inspired by Bigtable, and I was wondering if there was a direct correlation between, okay, Percolator, and then we try to do coprocessors.
Well, I think I did mention that in an earlier slide.
Sorry.
It is, like HBase, like Hadoop, this is inspired directly by Bigtable coprocessors. So, going from Jeff Dean's Lattice 09 talk, where he goes over it in a couple slides, we've taken those same ideas and applied them to HBase.
Hey, I'm interested in learning a little bit more about the Zookeeper Kerberos connectivity that you built in.
Mm-hmm.
Is that usable by non-HBase clients?
Yeah, it's general client-server security implementation in Zookeeper, so it's completely independent of HBase. We just needed it ourselves for the HBase security implementation. But you can track that in the Jira is Zookeeper 938. So go there for the latest information on it.